Hello, dear Space Talk viewer. Today I have the pleasure to introduce Mr. Tommaso Vergine, who will speak during this Space Talk about ASIC. He is considered as an expert for analog ASIC design at IC'Alps, company located in France. Tommaso has done his study in Italy and has received PhD degrees covering all aspects related to the design of IC, considering radiation effect. During this period, he started collaborating with CERN at Geneva, designing analog and mixed signal IP for high-energy physics experiments with radiation tolerant up to 1 gigarad. In 2016, he joined the CERN microelectronic group to continue to design radiation-tolerant analog blocks. Finally, since 2019, he is an analog and mixed signal IC designer at IC'Alps, where he worked on ultra-low power, low noise, and high resolution integrated circuits. It will allow us to well understand ASIC interest and key point for space application. Have and enjoy Space Talk.
IC'Alps is a French fabless semiconductor company based on Grenoble area with an expertise in design and supply of ASICs. We have chosen to operate across the entire ASIC value chain to provide our customers with a complete offering for ASIC development, from circuit specification, in-house design, up to the management of the supply chain. Of course, the aerospace is one of the industry we target with our custom solutions, but we are also active in other industries, such as medical, Internet of Things, or automotive. And by the way, our quality management system is certified according to different standards, like EM 9100, ISO 13485, and ISO 9001. And this is quite unique in our field. And one point I like to mention is that in the end, we have the chance to work with a large range of customer profiles, from startup to small and medium-sized enterprises and global leaders. Before we go into detailed explanations about the role that an ASIC can play in the field of the aerospace, let's start with the difference between an FPGA, an ASSP, and an ASIC. We all know that FPGA is the acronym of Field Programmable Gate Array, and it's essentially an integrated circuit which can be programmed and reprogrammed several times after the manufacturing to accommodate changes to a design or support newer applications. It can work, for example, like a microprocessor, a graphic card, both at the same time, just simply downloading a new configuration file into the device. This feature distinguishes FPGAs from ASSP and ASICs, which both, on the contrary, have fixed hardware functionalities that cannot be changed after silicon manufacturing. An application-specific standard part, or ASSP, is a general purpose integrated circuit that we can find on the catalog of electronic giants, whereas an application-specific integrated circuit, an ASIC, is designed specifically for one customer to provide the specific functions and performance required for the final application. So the choice between the three solutions can be dictated, for example, by your design type. Are we talking about a more analog or digital system? The performance required by your final application, and of course, your budget. To make a long story short, FPGA is an ideal solution to support development, prototyping, and low-volume deployment of many digital systems. Because yes, analog designs are generally not possible with FPGAs. However, if your design is permanent and does not require modifications, factors such as high unit cost and high power consumption may motivate a migration from an FPGA to to an ASSP or ASIC-based solution. I see four major reasons to consider a custom ASIC over an ASP and FPGA. The first is to miniaturize your system, reducing the bill of material and the weight. The second, to better protect your IP, making the undesired copies harder. The third, to boost the overall performance, as it's a more power-efficient approach and allows the integration of more complex and accurate functionality. And finally, the long-term supply commitments of ASIC design houses. In my opinion, the best strategy is to reply to the FPGA end-of-life events. The good news is that the access and development costs of an ASIC have been gradually reduced in the past years. And today, even companies with small to medium volumes can leverage the benefits of custom ASIC solutions. To be honest, I see two main constraints to the use of an ASIC: reusability and level of involvement. As already said, ASIC means application-specific integrated circuit, and this implies almost no chances to reuse your circuit in a new generation of products or for a new product line. So if the specification of some already existing components are okay with your project, I would rather recommend to go for this solution, as it will save your time and you can reuse it more easily. And the second thing you need to know is that development of an ASIC is like a team sport. It requires a good cooperation between people working both at system and circuital development level. And this is true for all the production phases, starting from the specification, passing through the design, packaging, the validation, and the industrialization of the circuit towards its final production. Let me give you the example of the IC packaging, which is a crucial step for the entire ASIC design. It must be thought upstream to be at the service of the final application. It means that the size, the performance, the heat dissipation, the pin-out, and the other constraints similar to these must be addressed as soon as possible and with trusted supply partners. The main challenge faced by ASIC designers is to guarantee device functionalities, performance, and reliability under a set of specified conditions. For example, temperature, operating voltages. For space application, this could be even harder to be guaranteed. Indeed, electronics must be able to cope with a radioactive environment that can cause damage to devices over time and failures. The trend in recent years is to avoid using space-qualified manufacturing technologies, essentially for their costs, and to use instead commercial technologies made rather by design. In general, there's not a recommended process because each technological node has its pros and cons. And to better understand the criteria for choosing one rather than another, I need to address briefly the nature of radiation-induced effects on silicon. We can classify the effects in two families: the cumulative effects, commonly identified as TID effects, total ionizing dose effects, which are due to a prolonged exposure to a radiation source, and the effects stochastically generated, generally referred as a single event effects, SEE, linked on the contrary to the probability of an incoming charged particle of flipping a logical state, which sometimes could be even a destructive event in the case of electrical latch-ups. To mitigate the first category of effects, one of the most effective workaround is to differently draw the layout of our transistors, using different geometries, non-standard geometries, like the so-called enclosed layout transistors, ELT. This drastically reduces the analog performance degradation. Concerning instead the single event effects, a way to face them is to use the triple modular redundancy. Essentially, we triplicate each memory element in our system and put to the vault the stored information. Now, at this point, we have some guidelines for choosing one manufacturing process. As we said, the nature of our ASIC, more analog or digital. For example, for an ASIC dominated by analog features, a relative mature node could be probably better. We do not have all those geometrical limitations typical of more advanced nodes, and this facilitates exotic layouts, in quotes. On the contrary, a more scale technology, allowing a more dense integration and increased system complexity and reduced cost per transistor, should be chosen for more digital applications. The second criteria for choosing a manufacturing process is its availability with respect to the application, with respect to the final application pipeline. The third is the intrinsic radiation hardness of the process, if any. And the fourth, the availability of some particular simulation models that can incorporate and anticipate the already measured radiation effects on silicon during the ASIC design phase. Just like any other application, the choice of the technology and the testing partners is extremely important. It should be done as soon as possible, ideally during the phase of the ASIC specification. Although the choice of the technology is crucial to identify the best strategy for achieving the desired radiation hardness, keeping the test partners in the design loop is also important for anticipating and optimizing the final ASIC qualification. The common point behind more or less all the space application is the harsh environment in which the electronics need to perform correctly and survives. This requires a particular care during the final ASIC qualification and screening. To assert whether a device is suitable or not for a particular application, it's often needed to perform a wider range of tests and inspections compared to those that manufacturers usually perform. This is why we lean on partners that have this expertise, partners like ALTER Technology. I will just mention one, which is extremely important. Be able to translate the system and environmental constraints into ASIC needs without overstressing the final performance, which could lead to a non-optimized design. This is the starting point of our collaboration, helping in writing the ASIC requirements. IC'Alps supports your team in gathering system requirements and translating them into ASIC requirements or specifications. In general, we do that for any customer, whatever the application, as the ASIC will be designed to fit exactly with the target application. Let me explain how it works. A team of experienced engineers provides generally in a time frame which goes from 1 up to 3 months, a report that covers ASIC potential architectures, reachable performance, estimation of silicon area and power consumption, risks and opportunities, suggested supply chain, development and industrialization costs. Then we take a deep dive in understanding your electronic system, meaning constraints at the bill of material, use cases, operating modes, but also required interfaces and PCB schematics. Then we define the different scenario of circuit integration. For example, hardware software partitioning or partitioning of functions into several ASICs. We also provide a first evaluation of the performance based on the simulation of some critical blocks. And of course, if you need it, we can recommend a supply chain for manufacturing the circuit. I think that it's essential to break down the community barriers to new actors if we want to develop more the ASIC market, especially in high reliability applications. The extra risks associated to an ASIC can be easily managed with the right strategy in terms of ASIC design, technology process, and test partners, etc. This can really make your product stand out.